Good morning, everyone. I am Farah Deeba, Assistant Professor, Assistant Board PG Autonomous College. I am going to take lecture on laser and holography, which are the contents of optics second. Optics, which is a branch of physics and a science of light. Here, laser and holography, everyone has idea about laser. They must have seen the pointers and the toys containing laser light, and everybody is familiar with the holograms using in the books or the concept of holography which are celebrities used for the entertainment and stage shows. So I hope you will enjoy learning laser and holography through this lecture. In this lecture second, I am going to discuss the devices which are used to prepare laser light. And the type of lasers here we are going to discuss are crystal laser, case laser and diode laser. And their examples are ruby laser in category of crystal laser, helium and neon gas laser, and in diode laser we are going to discuss semiconducting lasers. And the last we will discuss about the materials used for semiconducting lasers. Ruby laser. Ruby laser is a L2O3 docked with chromium ion. This ruby laser is a crystal laser which is first discussed by Ali Jawa, or this is the first crystal laser, and this is very expensive laser because we are using here ruby rod L2O3 which is docked with chromium ion, which gives its characteristic color, that is the pink color. And this is very familiar in jewelry also. We use this stone in jewelry. Here we are using a ruby rod of approximately 5 centimeter in length and 1 centimeter in diameter. This ruby rod is seen here. This is the pink rod which is placed in a system and which is surrounded by some tube, white color tube, where xenon gas is filled that produces a flash and that helps in optical pumping. And this whole system is placed in a hollow-like structure where liquid nitrogen flow is maintained to control the heat. So this is the construction of ruby laser, and how it works. In this, chromium ion has the property to get excited and generate metastable states for population inversion, and that population inversion helps to achieve stimulated emission, and hence the laser action occurs. Since this ruby is very expensive, so this crystal laser is very expensive. It has some drawback also because it gets heated and cracked since the flash which is produced by the xenon gas and the chromium ion is going to absorb only two wavelengths, that is a wavelength corresponding to the blue light and corresponding to the green light. It is absorbed by the chromium ion to get excited, and rest of the wavelengths will remain in the system which produces heat. So liquid nitrogen flow is maintained here to control its heat, but um, sometimes it's get cracked, and that is its main drawback. And being it is very expensive, we can not frequently change this tube. So when the time span, another Ali Java and Marman itself discuss another type of lasers, and that is the gas laser. So to discuss its working, we'll go to the three-level energy diagram in the next slide. We can understand its working through its energy level diagram, and this is three-level system. How we can understand this, the ground and the excited state of the chromium ion. Here we can again see how this excitation occur. If it is mentioned 420 nanometers in blue, it means blue wavelength absorbed and get excitation, atoms get excited, whereas few atoms absorb 550 nanometers and it can get excited. And the transition you can see here, spontaneous emission occurs after picoseconds, and you can see that chromium, all the atoms which are at this level 3.29 centimeter inverse, will come down by triggering, and the stimulated emission occurs, and a red photon or red laser light is obtained, which corresponds to 694.3 nanometers or 692.8 nanometers. They are the close wavelength, but they are corresponding to the red color. That's why red laser is obtained. How we can see this is system? We can understand it from here. Pink, green, and green. One is a ground state, the other is a metastable state, and the topmost is the excited state. So, a stimulated emission occurs where the red arrow is shown. It means red color obtains from this type of transition. In ruby laser, as I already speak, it is a crystal laser. It gets heated and cracked, so it is very expansive. So one more thing, if we trace a graph between the time in nanoseconds and the intensity, so in few nanoseconds the intensity goes very high, and in few further nanoseconds the intensity becomes low, because when we talk, it's a three-level system, so it automatically comes down, then again raises by oscillations, and again it will come down. So spikes are formed in ruby lasers. That spikes has utility in medical sciences, as this ruby laser or ruby spikes are used to treat or destroy the cancerous cells in a human body. So it is helpful in medical sciences, but in the laboratories it is not used properly because it is very expensive and the bands are not continuous. So replacing such type of laser, gas lasers are used, and the best example for that which we are using frequently in the laboratories are helium neon laser. We use helium with neon because their excited states are same, and helium easily transfers its energy to the neon by collision, and the ratio of helium neon in a tube is 10:1. So it is first discussed by Ali Jawab, and it is a four-level system. We can understand its working through, first of all, we can understand its diagram. It is its diagram. Again, a tube is taken whose length is integral multiple of lambda by 2, or approximately 5 centimeter tube is taken here. And here the pumping is electrical source of pumping. In the ruby road, that is the optical pumping, we use xenon gaze and the flash is produced. Where in this type of laser, electrical pumping is done, through which excitation occurs in helium, and helium on collision transfers its energy to the neon, and neon has a characteristic to generate metastable states, and finally population inversion occurs and action for lasers is achieved, or we can say laser light is obtained. So again, for oscillations, one is highly reflective, one end of the tube is highly reflective and the other is partially silvered, through which we can obtain the laser beam. So this is the basic diagram of the helium neon laser, and you can understand from its energy level diagram. Here we can see helium atom and neon atom. Both the ground and the excited states of the helium and neon are shown. E3 and E5 transfers its energy to the neon by collision, E3 to E5, and a three possible transitions are seen here. You can see E5 to E4, E5 to E2, and E3 to E1. So these are the transitions you can see from here: E5 to E2, E3 to E2. So these are the three transitions, and in all the three transitions, what we have seen here, the first type of transition from E5 to E4, the corresponding wavelength we obtain here is 3.391 micrometer, which is an invisible region. Again, from E3 to E2, the corresponding wavelength is 1.152 micrometer. Again, it is an invisible region. So the transition from E5 to E2, the wavelength which we obtain here is 632.8 nanometer. This is invisible region, means This is the red wavelength laser light we obtain here. So this is the laser action, and by the fast decay it will come to the E2 to this state, and again from this state again with collide with the walls of the tube, and it come to the ground state. So again the cycle will continue, being the oscillators we have taken. One is highly silvered and the other is partially silvered. So laser light continuously obtained from the partially silvered, and the process and the cycle continues. So this is the four-level diagram or four-level state diagram of helium neon laser is shown here. Here four different arrows are shown here. First is the pumping, and then fast decays, laser action, lasing action or transition. This way we obtain in the four state. We continuously obtain this thing, so we don't obtain spikes here like the ruby laser. We form a continuous beam. So such type of lasers are used in laboratories for practical purposes, and it has a wide application in research also. So another type of laser that is very cheap laser is the diode laser. This diode laser we can see in the pointers, or we can see in the toys also. So the function of this laser use the semiconductors, and these semiconductors are the compound semiconductors like gallium arsenide, indium phosphide, and so many examples are there. Here we have bands, we have energy bands, conduction band, and the valence band. We have holes, we have electrons, as we have discussed in the semiconductors. We should know the light emitting diodes means light emits from the barriers. In the same way, this diode laser works. Here, the concept of working as this reduced band diagram. Here, this stimulated emission occurs in the reduced band diagram, and this is the form of amplification. Here, light gets amplified. We can also understand this working through this thing through quantum well laser. Here again we have electrons in the conduction band, and we have holes in the valence band. P-type and N-type compound semiconductors are taken here, and they become this two. They are given in the form of faces or emojis, and the emojis are happy when the diagrams are reduced, and this amplification here occurs a lot. So this is the way where we can understand how the amplification occurs in the band diagram. The inversion condition in semiconductor lasers can be achieved by obtaining reduced band diagram. As we have seen in the previous slide, how this reduced band diagram enhances the stimulated emission. The electrons in the conduction band as well as the holes in the valence band will quickly move to the extreme of the bands corresponding to the levels E1 and E2 in the general four-level system. Quickly means within a time scale defined by the dielectric relaxation time. The smaller this time is, the quick action is vigorous. And this vigorousness is obvious in the reduced band diagram, and which is going to helpful the enhance the stimulated emission, which is the basic condition of laser. So this is the inversion condition and semiconductor lasers. In semiconductor lasers, um, we can see what are the examples of the same compound semiconductor we are using here are the gallium arsenide, aluminum gallium arsenide, gallium phosphide, indium gallium phosphide, gallium nitride, and these are the examples of semiconductor lasers in a compound form to amplify the light, that is laser action. Things help you to understand the mechanism and the process to prepare laser light in ruby laser, helium neon laser, and semiconductor laser. Thank you so much. To listen me, thank you so much.